Today we will pick up with the second half of, or the second day I should say, of Volume by Revolution. We're going to do one more day of this tomorrow. The video will be more along the lines of you guys practicing doing it, and then I will put up the answer afterwards so you guys can check your work. But this one we'll go through again together, making sure that you guys are understanding how to do it appropriately. So, it says find the volume if the region enclosing y equals x squared, y equals 0, and x equals 2 is rotated about the x-axis. So the first thing that you want to do is making sure that you understand what this looks like. So, y equals x squared goes to the point 0, 0, 1, 1, and 2, 4. Looks like this, something like that. Y equals 0 is the x-axis down here at the bottom, and x equals 2 is this line right here. So this is this area right here that I have highlighted. And so we are revolving it around the line, around the x-axis. So we're going to revolve it around this line right here, the x-axis. So remember, the first thing I want you guys to do is take the area and I want you to reflect it across the x-axis. So if I do that, it would look something like that. And we're looking at that area. So yesterday in our video, we talked about how the shape we were revolving kind of looked like a Hershey's Kiss. This one probably looks even more like a Hershey's Kiss, but it's kind of like a really, really wide Hershey's Kiss. It gets, really wide at the bottom. We'll do one in just a minute. I believe that it'll look more like a Hershey's Kiss in the actual dimensions of what they appear as. So let's get started. Once we're able to do that, first notice, by the way, that there is no hollow part of this shape. Everything is touching the x-axis. So because everything is touching the x-axis, we don't have a volume on the inside that we need to subtract away. Therefore, we just need the outside radius. So if I draw my circle, here's my red circle, and so the radius, big R, is represented by this red line that I've drawn in right here. So top function minus bottom function would be the line y equals x squared minus the x-axis, which is 0. So capital R is represented by x squared minus 0, top function minus bottom function, or just x squared. Now if you pull up our equations from yesterday, the one in the video from yesterday that we were using, if we don't have anything we need to subtract out the middle, then the volume is strictly represented by pi times the lower limit of integration, or the integral from the lower limit to the upper limit. So my lower limit in this case is 0, my upper limit is 2, so the integral from 0 to 2, of capital R squared. So if capital R is x squared, then this would be x squared squared dx. And again, remember where this formula came from if you forgot from yesterday. We are trying to find the area of one circle. If we can represent the expression for the area of one circle, then the integral will help us to add together the areas of all of the circles in between 0 and 2. So here is an expression for the area of one circle. One circle has an area of pi r squared. So we figured out an expression for the radius. Pi times that radius squared gives me the area of one circle, and the integral adds up together the areas of all of those circles. And we are not trying to be super duper calculators right now, so let's just get out our calculators and use them to find these integrals for us, just to make sure that we're practicing with our calculators and that we know how to do it. It's not necessary for us to practice all of these by hand. It would be a little tedious. So I'll pause the video and put it in my calculator. Why don't you do the same and then unpause it when you're ready to check your answer. Alright, so when I did that and I put that in my calculator, I got 20.106. Here's the next one. We're going to take that same shape, but this time we're going to revolve it around the y-axis. So if I can draw a rough sketch of it again, it looks like this. This triangular region with one side that's not necessarily a triangle. And we're going to revolve it around the y-axis. So my y-axis is right here. That means I want to reflect that shape about the y-axis. It would look something like this. And notice that if I do revolve this one, now I do have an empty hollow part on the inside. So if I look at the outside, here's my outside radius, so that circle that I just drew. And there's the red line to show the radius. So this outside circle, if I revolve the shape around the y-axis, I'm getting a cylindrical shape on the outside, similar to the one we looked at yesterday. The only difference is that here on the inside, notice that if I draw my green circle to show the inside radius, or the inside circle, all right, you guys can see here this green circle on the inside. Yesterday we were pulling out like a conical shape, a cone shape. Today it's more of a parabola, so it has much smoother edges that it's kind of pulling out from. So it is still a hollow shape on the inside of the cylinder, but the hollow shape is is shaped more like a parabola than a cone. So in this case, because we do have that hollow area on the inside, we need a capital R and a lowercase r. So capital R equals, remember that anytime we revolve around a vertical line, now everything is going to be in terms of y. So my limit needs to be in terms of y, my integral needs to be in terms of y, my functions need to be in terms of y, and my the limits of integration need to be in terms of y. So if I tilt my head to the right, anytime I revolve around a vertical line, I like to tilt my head to the right so that as I'm looking at my circles, I see this as the top of the radius and that this is the bottom of the radius. So the top of the radius is over here at the line x equals 2, and the bottom of the radius for the red one is at x equals 0. So 2 minus 0 is equal to 2, therefore my outside radius is equal to 2. For the inside radius, for the green one, if I tilt my head to the right, the green line right here for the inside radius touches at this function, which is y equals x squared, and then down here at x equals 0. Now remember, the problem is that we can't keep this equation y equals x squared in terms of x. We have to change it to be in terms of y. So I'm going to go ahead and change that really quick. And I'm going to rewrite this. Instead of putting y equals x squared, I'm going to take the square root of both sides and say that this is x equals the square root of y. Excuse me. Notice that I didn't put a plus or minus in front of it because this is only the positive half of that parabola. The negative half is the one that's over here. So since I'm looking at this one, I only want the positive square root, not the negative square root. So we're going to use that equation. So going back to looking at my green radius again. The top of the green radius is right here. And now that we've changed our function to being in terms of y, we can say that this line is represented by the equation square root of y, and that the y-axis would be x equals 0. So it's going to be the square root of y minus 0, which is just the square root of y. All right, beautiful. If I plug it into my formula, and again, this time, because we have that outside radius and the inside radius, and we have to subtract out the inside radius, we're going to have the volume equal to pi times the integral. Remember, it's not 0 to 2 anymore. Those are limits of integration in terms of x. Now that we're integrating in terms of y, we go from bottom to top. So the lowest y value in this volume is going to be at y equals 0. And then we go to y equals 1, 2, 3, 4. So 4 is the tallest y value in this problem. So we're going to integrate all the way from 0 up to 4 in terms of y values. And then remember that it's the outside radius squared, so 2 squared, minus the inside radius squared, so the square root of y quantity squared, dy. So my limits are in terms of y, my functions are in terms of y, and my integral is in terms of y because we are revolving around a vertical line. Go ahead and pause the video, put that in your calculator, and see what you get. I got 25.133 or 25.132, depending on whether or not you're rounding or truncating, but either of those is acceptable. All right, next problem. So this is a new shape. We are no longer working with that quadratic equation. This is now y plus the square root of x, and we're trying to revolve it around the x-axis. So I'm going to draw a quick sketch of what this function looks like. The square root of x shifted up 1 unit. This plus 1 right here is a vertical shift up 1 unit. So it's up 1, and then the square root looks like the hook function. So it looks something like this. Close enough. There we go. So it's bound by that function, 1 plus the square root of x. It's also bound by y equals 1, which is this line right here. And it's also bound by x equals 4, which is this line right here. So the area we're revolving is this area right here. And they're asking us to revolve it around the x-axis. So if I want to revolve it around this red line, that means I need to reflect it over the red line. So it looks something like this if I reflect it over the red line. And when I draw my circles to show the outside circle and the inside circle. You can see that on the outside, if I'm revolving this on the outside, the best thing, I'm trying to think of what this looks like. The only thing I can think of this looks like is it kind of looks like almost like a bullet, like that round shape of a bullet. But on the inside, it has this cylindrical shape cut out of it. So kind of like that they stuck a straw through the middle of it and cut out the middle of it. And it's not exactly like that pointed shape at the top either. It doesn't finish there. But anyway, it has that rounded-ish shape on the outside that you might see that way. And so, again, this is a washer because we have an outside radius and we have an inside radius that we're taking away. So we need expressions for both capital R and lowercase r in this case. Now, capital R is the red one. So going from top to bottom for my radius. Remember, my radius doesn't go all the way through the circle. It only goes halfway through the circle. The top of this function is 1 plus the square root of x, and the bottom of this function is 0. So 1 plus the square root of x minus 0 is just 1 plus the square root of x. And lowercase r is the inside radius, this green line over here. So the inside radius, if I look at top function minus bottom function, the top of that green line is at 1, and the bottom of that green line is at 0. So 1 minus 0 is 1. Now, I'm just going to start doing some shorthand, if that's okay with you guys, because on the AP test, this question will probably appear in the calculator section. It might appear in the non-calculator section, but most likely it'll appear in the calculator section of the free response questions. When you do it, similarly to how we talked about with area, is that I don't necessarily need to write out the entire volume formula with the r's in there. If I write it like this, as long as you write volume equals pi times the integral from, and since we're revolving around a horizontal line again, everything is in terms of x. So my furthest point to the left is at x equals 0. My furthest point to the right is at x equals 4. So from 0 to 4. And then notice that I'm just going to put r squared minus little r squared dx. As long as you write that, and as long as the reader can find somewhere where you wrote capital R equals blank, little r equals blank, then that's fine with them. They don't need you to plug in right here 1 plus the square root of x. They don't need you to plug in here, right, 1. So this way, if you want to, and it's not necessarily shorter or longer here while we're doing the notes, but it could save you a ton of time on the actual AP test. If you just input like this outside radius to be y1 and the inside radius to be y2, it can save you some time in actually putting together the problem. So it's up to you on how you want to write it, if you actually want to plug in capital R to be 1 plus the square root of x, or if you just want to leave it as capital R, but that is enough work to say that you know what you're talking about. So however you need to do it, go ahead and either plug these into your calculator and figure it out, or go back to writing it the way we were doing it originally and then plug it in your calculator. So pause your video, go ahead and evaluate this, and then we'll come back together again. When I did this, I got 58.643. All right, same shape, but new line that we're revolving it around, so let me sketch it one more time. All right, so there's my shape. This time we're revolving it around the line x equals 4, which is a vertical line. So notice that for this piece of our problem, everything should be in terms of y because we're revolving around a vertical line. So let me show the reflection of what this looks like if I revolve it around this vertical line. Notice that there is no holes in the middle of it because this entire shape touches the axis of revolution. It's touching the line that it's being rotated around. So there is no volume in the middle I need to subtract out. Therefore, I just need a capital R. I do not need a lowercase r. So I'm going to draw in my radius to see the expression I need to find for that radius. I'm trying to think of what this looks like. It's kind of like a little mound, like a mound of dirt, I guess, if you will. That's what it looks like to me. But if I am trying to find an expression for that radius, tilt your head to the right. Remember that everything needs to be in terms of x. So right now this equation is in terms of, everything needs to be in terms of y. And right now this equation is in terms of x. It's y equals 1 plus the square root of x. So I need to solve this equation for x and isolate it so that I can get my equation to be in terms of y. First thing I'm going to do is subtract 1 over to the other side. So y minus 1 equals the square root of x. And then to isolate x, I'm going to get rid of that square root by squaring both sides. So I get that x is equal to y minus 1 quantity squared. So now that is my new expression for how I'm going to represent the this line in terms of y. So again, coming back to this red function, because I want to know what the length is of this radius that I've drawn right here in this red line. So top function is x equals 4, and the bottom function is x equals this, y minus 1 squared. So my expression for the radius is top, which is 4, minus bottom, which is y minus 1 squared. 4 minus y minus 1 squared. And then again, we're going to calculate volume. Volume is pi times the integral. My limits are in terms of y now, so I'm no longer going from left to right. I don't want to go from 0 to 4. I want to go top and bottom. So from the very bottom, the lowest y value I see in this volume is at 1, and the tallest y value I see is at 3. So I'm going to integrate from 1 to 3. And then remember, I can just write capital R squared dx, and that is enough work for my reader to understand that I know what I'm talking about, because they'll go and search for what I defined R to be, and as long as I defined R to be the correct value, then that's fine. I like writing it separately sometimes just because I think our brains think kind of in one way sometimes, and so if you're able to write this radius, sometimes you're going so quickly, whether or not it's on a test or on the AP test for that matter, that when you transfer it, like if you actually tried to plug this into the equation and write out the volume with this plugged into it, a lot of times you go so quickly that you make mistakes, and like literally you accidentally might write a plus instead of a minus, or you might forget a parenthesis, and every single time you make a mistake like that, if the equation is not correct, they have to dock you points. So please make sure that you guys are either number 1, being very careful when you're doing it, or number 2, become satisfied with the fact that you can leave them separately. Like if I can write the equation of the volume and somewhere else I've written what R is equal to, that is enough for the reader to know that I know what I'm talking about. So pause your video, put that into your calculator, and check your answer. I got 53.616 or 53.617 depending on truncation or rounding. All right, here's our last one for today. Example 6, it says find the volume of the region enclosing y equals x squared, which we have looked at already today. Ooh, let me draw this a little bit bigger. So just to give you a general idea of what y equals x squared looks like, it looks like this. And to give you a general idea of what y equals the cubed root of x looks like, which you learned back in IM3, it looks like this. So the only region that's enclosed by these two graphs is this region right here, where in between 0 and 1, where they cross each other. So I'm going to redraw this, but I'm going to redraw it a little bit bigger with those being my predominant things that you can see. So from 0 to 1, that's literally the only y equals x squared looks like that. And y equals the cubed root of x looks like this in that region. So that's what I got. This is the area that I am rotating. All right, so we are going to rotate it about the x-axis. So I need to revolve it around this line right here. So first thing I want to do is I want to try and reflect this shape as best as I possibly can over that line. Looks something like that. Not perfect, but something like that. And I'm going to do that because it's going to help me to visualize what this shape actually looks like. So there's my outside circle. Notice that it does have a hollow part on the inside. There's my inside circle. I'm trying to imagine what this actually does look like. If I'm tilting my head to the side to look at it, it kind of looks like a bowl, possibly. Like on the outside, it's like this bowl shape. On the inside, it's like a funnel that's being taken out. So on the outside, it's like a little bit more round. And then the inside, we just took out the volume of a funnel. So that's the best I got to describe what that looks like. So we're revolving around a horizontal line, which means that everything's going to be in terms of x. So if I'm looking for my expression for my capital R, this red line that I just drew right here, it's the top function minus bottom function. So that is going to be, the top function is the red one, the cubed root of x. So this is the cubed root of x minus 0, which is just the cubed root of x. And for the green one, for my inside radius, it's the top function minus the bottom function, and the top function is this black one, which is x squared. So it's x squared minus 0, which is just x squared. And again, the reader is 100% satisfied if you just write that the volume is equal to pi times the integral from, they intersect at 0, and then they, excuse me, intersect again at 1. So this is from 0 to 1. Capital R squared minus little r squared dx. And again, the reader is 100% satisfied with that. You do not need to, let me erase this. You do not need to plug them in. So pause the video and go ahead and evaluate this and check back in when you have your answer. So when I plug these in, I got 1.256 or 1.257, depending on how you're rounding your answer. All right, that's the end of the video for today. Tomorrow we'll come back and do some more ones where you guys are practicing a little bit more, and then I'll just put the answer up afterwards.